Okay. Share my screen. Okay, so we're still missing about 6 students. Let me wait another 30 seconds. Time is now. Okay. Normally we had a more at this time. It's week 6 now. Over half of the quarter has been done. Went by so quickly. Okay, let's get started. So this class is about irradiation and microwave. So I moved a part of the irradiation to this class and talked about spray drying in the last lecture. So I hope this combining these two talks won't make us too rushed today, because I did cut a few overlap the slides. I guess from 204, so that will focus on those new concepts, mostly on the microwave part. So before we start, let me quickly go through the survey results. I did a look into all of your slides and all of your response. There are still I think 5 or 4 students didn't submit the survey. I mean, it's extra credits. If you still want to, provide me any feedback, I'm willing to reopen the survey for you. The reason that I set the deadline so early is to to get the information as quickly as possible. So because it's already halfway through the quarter, so I can um, take some action based on that. So some very common comments are sometimes I went too fast on some topics, and especially those calculations and showing demos of those Excels. Um, so I think so yeah, the first time I think I wasn't sure that how well you or how familiar you are familiar with the Excel plotting. So a lot of functions that I could have explained more in details. And also many of you want more calculation problems and use the Zoom whiteboard. That's a great comments. I think I will try the Zoom whiteboard. It seems that allows me to write it down so I can solve the problem with you the same time instead of doing all the math before the class. So that's a good call. And also more homework. That's easy. Okay, so more homework. I see not just one response, but several students mentioned that more homework. Um, I mean, that's definitely work. And also, some of you mentioned that the homework, the due date is too long. So especially for the last exam, you wanted to see the key before the exam of the calculation question, so that it will help with the exam preparation. That's true, but for that type of question, 1 week is I think is reasonable. If you want the key or want to check your answer, you can always come to my office hour. And also because the quarter runs too fast, sometimes if um, we have to wait until posting all the keys to the homework, that will postpone our exam time. So next time regarding those big homeworks, I will definitely post a key before exam, but also I encourage you to check your answer with me in the office hour. Okay, and also more discussion during the class by doing more breakout rooms. I think that's also a good suggestion. So yeah, that's all the major comments I received. I think that will definitely help us um, to teach this class more efficiently. Okay, so also I got some questions about the seminar this Thursday. So this Thursday, the seminar will be um, group presentation. So you have to select the topic. So now we have 5 lab reports and 4 seminars. And so you can pick 4 topics out of 5. So for example, the following one, you can choose from the retort and ice cream making. I think many of you have already chosen. And the time will be 10 minutes, and there will be 3 to 5 minutes of Q&A session. And there's some potential content to cover, okay? Something like introduction, background, the history of this technology, market size, those are general information. And then you can present the results and findings or some take-home message from experiment, and also link to the current industries such as commercialized products. What are their limitations and the trend? And also you may cover the recent research and innovation activity on this topic, can be either from academia or either industry. And also there you can also randomly present any thoughts, ideas from your group. Okay. And you can present everything. You can have one person presenting everything, or you can split the work. So every student will present 1 to 2 slides. So either way will work, because finally, I mean, you'll get a peer evaluation within the group. So you guys know who contributed to which part. So based on your contribution, your group member will evaluate you. So I think some of you prefer to find those information or making slides. Some of you prefer to present. I mean, that's okay. That's you guys can assign those rules inside the team. As long as the final deliverable looks good, they'll be fine. And also the evaluation. So basically, we'll have peer evaluation. So each group will rate each other, and based on the rubric. Okay, so the final score will be 25% from 3 groups of rating. So basically, after the presentation, you guys will, I will put you guys into breakout rooms. So you guys will, discuss, maybe share your scores with group members, and finally one group will only give me 1 score. Okay, and also combine 25% from myself. It will be your final score. Okay. Okay, so any questions about the seminar on this Thursday? Okay. All right, so this class will be talking about irradiation and microwave processing. So in the 204 class, we covered one topic that is called alternative processing, right? So if you look at this electromagnetic wave chart, you'll find that almost every single wavelength here can be used as the alternative processing tool. For example, the microwave, which we'll be talking about today, has a wavelength of 0.01 meter, okay? That's in the size of butterflies. And also for those irradiation, those will be very short wavelength, but high energy density electromagnetic waves, like ultraviolet, X-ray, gamma ray. So those represent 2 categories of those waves. So either of them, we can use them for alternative processing. Okay, so but they have different mechanisms. So for long wavelengths, for example, radio frequency, infrared, microwave, they actually are increased molecular vibration. Okay, so we know that from chemistry, the temperature of a subject is dependent on how fast its molecule, the molecules moves, and also that's called thermal energy, right? So there are two ways we can heat up foods. The one way is to give it heat, for example, using heat transfer by conduction, convection, or irradiation, right? Another way is that we kind of generate more vibration internally instead of transfer the heat. We let the molecule to generate heat by itself. So in that case, we'll be using something like those long wavelengths of electromagnetic waves. And the purpose here is to increase temperature. However, in the short wavelength case, for example, X-ray, ultraviolet, gamma ray, and they actually are killing the bacteria directly. So in first case, we are raising the temperature to kill the bacteria. But in the second case, we actually destroy the bacteria by breaking their DNA. Okay. So some of those techniques like ultraviolet UV light is very common in sanitizing the surface in hospital or those food production manufacturing plant, right? So so as I mentioned, in the radio frequency, we're actually applying the wavelengths that causes the resonance between those molecules, so that the vibration becomes uh, more more intense, and that will increase temperature. But on the other hand, if we apply a very short wavelength, that can actually interact directly with the DNA and other large molecules by cutting it through, um, and that can cause direct damage to kill those bacteria. So those are the main mechanism difference. So in the irradiation that we'll be talking about today, we're actually applying the energy to generate the free radical. So there are two mechanisms in the irradiation. The first one is called the direct effect, which means when the cell is hit, the energy, because we know that irradiation, although it doesn't convey too much of the heat, but the deposition of energy can still cause the damage directly to the pathogen. The second scenario, which is indirect effect, is actually more common. So the DNA is actually destroyed by the free radicals. So basically, if we use the high energy wavelength to apply that to water, they will create something called a free radical. Okay, so that's actually the mechanism when we applying the UV light to accelerate a lot of reactions. For example, if we put a lipid under UV light, then the reactivity will be built up much more quickly than without UV light. The reason is that those high energy wavelengths actually can generate a free radical. And you guys know that free radical is highly involved in the lipid oxidation process. And also that can interact with the DNA. And that's part of the reason that if we get X-ray too often, we'll get the cancer will more easily to happen, because we are actually damaging the DNA, cause those mutations. Okay, so as I mentioned, in the irradiation, we are using more on the right side of those radius, of those wavelengths. We can either use ultraviolet, okay, X-ray and gamma ray. So gamma ray is the most intense and most dangerous one, with the highest amount of energy. So there are some examples where we apply the irradiation in food processing. For example, the tomato the potato always have those sprouting issues. Okay, and but when we apply um, some irradiation energy, then the sprouting can be inhibited or slowed down. Okay, so but actually that requires quite a very small. Actually, this is a very small amount of energy, 150 calorie. So here you can see we apply different amount of dose to reach different purpose. So you can see most of the unit here is the kilogary, which is 1,000 greater than the one that you just saw. So the one previously for the sprouting is just a 0.15 kilogary. And here, if you see, if you want to reach completely sterilized product of the packaged meat, we need 44 kilogary. That's a huge amount of irradiation. Okay. And for example, if we only need to control salmonella in fresh egg, that will only require 3 kilogary. So really depending on the purpose, we apply different dosage to the irradiation. Any questions here? So there are some advantages and disadvantage of irradiation. So first of all, it's a non-thermal process, right? We don't apply any heat. So which means that the nutrition loss will be minimized, right? And also that only take a few seconds, right? Because we can apply a huge amount of energy within a few seconds and then to kill all the pathogens. And even the food is packaged because our the electromagnetic wave has some penetration so that the package will not inhibit the heat penetration or something like that. But disadvantage is that it's huge. The capital cost is huge, right? Because there are a lot of safety issues in regards to protect the personnel from being hurt, and also uh, those facilities are very few in the United States. And another disadvantage is that we are causing some flavor problem because of the oxidation. Remember that a lot of free radicals will be generated to accelerate the lipid oxidation. So those will cause some um, unpleasant flavor generation in those irradiated foods. So can you guys come up with other advantage and disadvantage here? Because the list here I put here is not complete. Any other thoughts?
Consumer perception of irradiated
Yes.
foods.
Good call, Lauren. So consumers right now are still not completely accepted by those um, irradiated foods, right? People usually will link it to the nuclear or the all those dangerous stuff. Good call. So consumer exception. So typically those irradiated foods are usually for those special use. For example, those astronaut foods, right? So any other problem with it potentially, or any other advantages? So how about um, can we use the irradiation to sterilize large bulk of foods like because we know that the wavelength is so short for those irradiation wavelengths. And typically, you guys learn from physics, right? So the shorter the wavelength, the less penetration depth, right? So in that case, our packaging material has to be very thin Otherwise, for example, if we have um, a large box of cheese, and then inside those large box we have smaller package. In that case, the irradiation might not be able to penetrate um, the package. And the other thing is that in the sterilization retort, we can monitor um, the temperature change inside the can to see if that reached our desirable D value, right? The F value. Um, but in the irradiation, it's quite difficult for us to see whether our process is sufficient, and if not, what would be the sufficient dose, right? We have to do all the microbial tests to see how much microbial is survived. So that's also part of the um, disadvantage of that. It's hard to evaluate because it's like a black box. You know, you treat it and then it's done, right? Although we can put um, those detectors to see how much irradiation has been penetrating, but that cost is it will be huge. Okay. All right. So our next topic is about microwave, which is our focus today because it's more applied in the food industry, and we are seeing this more and more common in a lot of different applications. So in definition, a microwave are the electromagnetic wave, which the frequency is from 300 mega hertz to 300 gigahertz. Okay, so you guys know that how to convert the frequency to the wavelength, right? Basically, you use the the speed of light divided by the frequency, you get the wavelength. So I'm not going to cover that part. Okay. So domestic microwave appliance, basically those we using at home, the frequency is generally 2.45 gigahertz, but those industrial ones can be either 915 megahertz or 245 gigahertz. Okay, so industry sometimes use even more longer wavelengths to penetrate more greater depth. Okay. So microwave, it's very similar to infrared and the radio frequency. Okay, so basically they interact with the water molecule to increase temperature, and really depending on the wavelength that we're applying. If we apply a long wavelength, then the penetration depth will be longer. We'll cover a lot about how the penetration depth is affected, and I'll show you the equation, how is that calculated. So don't worry if you don't understand here right now, okay? So typically long wavelengths will result in deep penetration, and short wavelengths will be resulting only in surface heating, okay? So actually we will have our lab this Friday, and also we'll measure the penetration depth. It will be a very interesting lab. Okay. So before we start jumping into the microwave processing, first I want to talk about what is dielectric property. So have you guys learned about what is dielectric property before? Oh, never? Okay. So this is a very physical chemistry terminology, and it's not easy to explain. But here I will make it very simple. So the dielectric property means in the microwave um, field, people usually, because the microwave, the food scientists, they are also not a physical chemist. So basically, there are a lot of definitions. So the definition we use here is that it's the ability of the material to convert the microwave energy to heat. So I guess some of you have learned about some type of material like water is a very good heating medium in the microwave that can absorb a lot of energy, right? But some type of material like metals, sometimes I put a aluminum foil mistakenly into the microwave, and then after that you'll see that the foil is not heating at all, but it's causing some sparkling, right? Some that stuff. So that has quite different dielectric property compared to water, which I'll show you a table comparing the dielectric property of different materials. Okay, so within the dielectric property, there are two parts. The first part is called sometimes called a real part. It's termed as the dielectric constant. Okay, so this is the part that signifies the ability for the material to store electric energy. So a lot of conductors, they actually they have pretty good dielectric constant, right? So the sparkling that you see when you are microwaving those metals, it's actually because of the generation of those electric field. Okay, but in the other case, the second terminology is the imaginary part. Okay, it's usually represented in plural. Okay, and and this is called the dielectric loss, which is the which shows the ability to convert the electric energy to heat. Okay, so a lot of the cases we don't have good dielectric loss, which means the electric energy will be will not be converted to heat. Okay, so it contains two steps. First, it has to go to the generation of the electricity, and second is the electricity to heat. Okay, so here is the equation. As you can see that, so the epsilon star is the dielectric property. Okay, and then epsilon dot one prime single prime that shows the dielectric constant. And then the second terminology, which has a plural, that shows the dielectric loss. Okay, the epsilon double prime. So typically, those values are measured by experiment. So there's no way that I will let you to calculate what is the dielectric constant here. So all those values are measured, okay? And even for the dielectric property, it's also measured, okay? I will not show any questions or problem solving asking you to solve this equation, okay? So here I want to show you a few, another terminology is the more commonly used to compare the difference between the dielectric loss and the dielectric constant. Okay. So if you guys still remember, the dielectric constant is that converting the microwave energy into electricity, right? And then dielectric loss is the ability to convert electricity to heat. Okay, and the tangent delta means the ratio between those two abilities. So here's a question. Do you think a larger tangent delta is better for microwave heating, or smaller tangent delta is better for microwave heating? Any thoughts? Okay, maybe let me explain again. All right. So so the dielectric property, okay, so this is the terminology, this is the microwave explanation, okay? So we have two parts, right? in if so first let's forget about this question. So we have two parts of this property. The first part is the dielectric constant. Okay, so the dielectric constant is to store the electricity. Okay, so basically it's converting the microwave energy into the electricity and store it. Okay, and the second part is the convert the electricity into heat, but it's called a dielectric loss. So in microwave heating, we need to generate heat, right? So which means we want a high dielectric loss instead of the electricity is being stored there, right? So typically we want a large epsilon double value, the dielectric loss, to convert more energy to electricity to heat, and a smaller dielectric constant, which is the ability to store electricity, right? Which means that they will retain the electricity from converting it to heat, right? So we want, so a good microwave material like water will have a good high dielectric loss value, okay? So which is epsilon double prime value. Is that clear, guys? Good. And then if we look at the tangent delta, we can see that the dielectric loss, which is the value we want to be larger, is on the top, okay? And the dielectric constant value is on the bottom. So in this case, we know that the larger tangent delta means the means it's a better microwave material, okay? So for example, if we look at the table on the right side, aluminum foil is the one that I mentioned that we should not put them into the microwave, right? Because they they it cannot convert the electricity into heat, so that all the electricity, all the electrons, they cannot accumulate in those spots and generate a huge electric field, and then can cause some dangerous sparkling and fire, right? So if you look at its loose tangent value, it's 0.0006. Okay, so which means it's barely heating up. Okay. However, if you look at the beef, the beef in raw, they have both. So first, if you look at the loose tangent, it's about 0.3302, which is about 500 times. Is that 500, 5,000? I never mind. It's hundreds thousands times greater than the alumina. So which means the ability of the raw beef to generate heat under microwave, it's 600 times greater than alumina. Okay, and although it also has a good dielectric constant, but still a lot of those electricity can be converted to heat. But beef also tend to store some. Okay, so in this case, if you find any material is large in loose tangent here, for example, raw beef, blood, and if you all come all the way here, egg white is pretty good, okay, and the fat, lung, and the those are all very good material to be microwaved, okay. But if you look at those very small values like alumina, those metals, okay, such as glass, okay, and here like soil, sandy soil in dry, and the quartz, which is like glasses, and the ceramic, and the nylon, okay? So those are, and the Teflon, so those are very good, better material, okay? Even though we microwave it, that will cause very dangerous, the accumulation of the electricity on the surface of the material that can cause some damage. sometimes and can even cause explosion because there too much energy condensed on the material cannot be converted into into heat, right? If you it's like when the electric field is too large that it can penetrate the air. It's just like a thunder, right? So that will cause a huge damage to the microwave. All right, so that's about the tangent delta value and tangent loose tangent value, and how we use that to determine if the food can be heated well or not. So, any questions about this terminology here? Okay, so okay, no question. Okay, good. So and the dielectric property actually is affected by many factors. For example, temperature and the microwave frequency. So based on those, the difference between all materials when they are responding to the dielectric property, we classify them into three categories. The first category is that the material can absorb a lot of the energy, okay, and convert that to heat, like water or like beef, those high moisture content foods. And the second category is that they are transparent or has very low low electric loss material. Okay, so basically they don't store any electricity, and they also do not convert the electricity into heat. So those materials are in the secondary second category, which is very rare. Okay. The most common is the conductors, right? Those conductors, um, they actually they kind of accumulate all those electricity, but do not convert them into heat. Okay, so those are three categories based on the table that we have, you guys have seen. So here another example showing different foods. There are different dielectric constant and dielectric loss. Okay. So for example, you can see um, like depending on a lot of depending on the moisture content, okay, and also uh, the food composition. For example, the fat composition, water composition, and other macromolecule composition. You'll see different patterns. Typically, if you, for example, the pork, it has relatively small dielectric constant and uh, uh, relatively small dielectric loss. Especially if you look at the food, their dielectric loss are very close to each other, right? But on the dielectric constant, they can be one-fold different. So and if you look at the gravy, which has a lot of fat, the dielectric loss is a little bit higher than other material. Okay, but in general, the foods um, they are not very different in terms of the dielectric property, but they can still be um, if you because when we calculate tangent the loose tangent, you will use the upper value divided by the bottom value, right? So the you use the epsilon double prime on the top, no, epsilon double prime on the bottom divided by the epsilon prime on the top. So in that case, you see if you divided that, they will be quite different. For example, for water, it's about 10 here divided by 75. So it's relatively small when you compare to pork, right? For pork, because the denominator is much smaller, so there's still a two to three times difference. So later on in the penetration, we'll see how that will impact the how much microwave length microwave can penetrate the food. Okay, so So here I want to introduce one parameter is for helping us to evaluate how much energy can penetrate the food material. So this terminology is called power penetration depth. Okay. So because it's harder to define that how far our energy can go, because if you think about the energy, even after very long distance, you can still detect some wavelength, but it can decay a lot. So the penetration depth here is the is the depth where we find that the decay has reached the um, to a value where the power density drops to 37%, which is 1 over the natural log constant. Okay, so for example, the so here is a comparison between the two wavelengths. So remember, in the industry scale of microwave, we use two wavelengths, right? The first one is 2.45 gigahertz, or 2450 megahertz. It is more larger frequency, right? But smaller wavelengths. Okay, so in this case, you can see the penetration depth is very small. Okay, but on the other hand, if we use a very small frequency but a large wavelength, that the penetration depth, the X here, is much greater. Okay, so basically they're almost proportional. Okay, so here's a question. So if we have for large wavelengths, the penetration depth is so much better than the small wavelength. Why should we use small wavelengths? Uh, can we use like why can't we use like 300 megahertz or even smaller wavelength to heat up foods? What do you think are the hurdles there?
Would it ruin some of the sensory aspects of the food?
Sensory aspects. Miley, can you explain why do you think sensory aspects are will be impacted by the wavelength?
I'm not 100% sure, but
Yeah,
maybe
that's a
like
good guess.
those longer wavelengths
Mhm.
somehow not only affect like the microorganisms, but also affect some of the quality of the food. Like I don't, maybe the texture might change.
The texture might change. Um, yes, I think the texture, we'll talk about it in the baking, that the texture, especially for those baked material, you want the surface to be like a crust, right? And if the penetration depth is too long, then probably the inside you form a crust, but outside is still soft, right? So that's probably, yeah, that's a pretty good guess. Um, the sensory property, especially texture. Good job, Miley. Any other thoughts here? So for example, if you think about, you guys probably it's quite old-fashioned stuff. I don't know if you guys still listen to the radio. So the radio has a very, very long wavelength, right? And then it can penetrate almost everything. When we are inside the building, the wavelength, the radio frequency can still penetrate all the walls. So what would be the problem if we use those high wavelengths of the wavelengths to process foods? It will be difficult. So what if we are operating the machine, but the all the electromagnetic wave is coming up to outside. You can, because first of all we need to contain those microwave inside the processing chamber, right? Otherwise, the personnel who is operating the machine will be cooked, right? So that's another reason that it's if we use very long wavelengths, although our penetration depth is very long, we can treat the bulk foods, but we can hardly contain them because they can so easily penetrate everything, right? So that's another reason that there's just certain amount of wavelength we can use, right? Okay. All right, so how to calculate the power penetration um, depth? So this is a very complicated equation, and um, and you can see, but if you break it down, you'll see that all the terminology, all the parameters here we have covered, right? Basically, you can find everything here from the tables before. So there are two steps involved in the calculation of the penetration. So first, we're calculating the um, the, the alpha prime value. So this value, sometimes we call, we name it, but sometimes it's just a, we don't name it because it's part of, um, because it doesn't have too much of the physical meaning, or the physical meaning is hard to explain. Uh, Most likely we directly use the second equation. So basically you can see they are very similar, okay? It's just it's flipped upside down, okay? So the z depth is, z is here, value here is the depth, the penetration depth, which is the, means the electric, the wavelength, the power density will drop to 1 over natural log here, okay? So um, so here you'll see that there are three parameters here. The lambda is the wavelength, right? And the epsilon one single prime is the dielectric constant, right? You'll find it from the table, and the loose tangent you can also find it from the table, okay? So for example, if I say I have a very, so first of all, if you have a longer, um, larger wavelength, the penetration depth is greater, right? It's completely proportional. And if for those, for the loose tangent value, for example, water or other material, they have large loose tangent value. And if you have large value here, the entire equation, the denominator here will also be bigger, larger, right? So that will cause the smaller penetration depth, right? And also if you have larger dielectric constant, that will also decrease the depth, the penetration depth, right? So this is something that you can directly find from this equation by eyeballing those interactions. For example, if you given the table with the property of material, for example, the dielectric constant and the dielectric loss, you can based on the microwave the microwave length, you can calculate the depth, right? It's actually a prediction value. But in reality, this value is highly impacted by other properties. Okay. So any questions about this equation? It should be very straightforward. It's just, it looks very complicated, but all the values you can find from those tables, they will be all given, right? So what you do is just to plug them in and do a simple calculation. It's just to make sure that you don't miss the like square root or those things. So it just looks complicated, but all the values are given. It's not like the retort calculation, one of the most complicated one in the food processing, because you need to, there are like 7 steps you to find the one by one, each by each, right? And a lot of them you have to deal with the data processing from those heat penetration curves. So those are very, so the equation here is less complicated compared to the retort one. Okay, so, but here, if you look at the same material, for example, water at 25 degrees C and the water at 95 degrees C, you'll see that their penetration depths varied a lot. right? So why do you think are they different? Because if you plug in the numbers, it seems they are all constant, right? So for example, water 25 degrees C, the penetration depth is 1.4 centimeter, but water at 95 degrees C, the penetration depth will be 5.7 centimeter. Why do you think they're so different?
Does it have to do with density of the water?
Density of water. Yes, Emma. So that's a good guess. So density of water, how much, Emma, do you know how much water density will change from 25 to 95?
Um, Not off the top of my head, no.
So some of the water property did change, right? And I think here it's not probably it's not the density because you don't in this equation because everything is calculated by this equation, right? You don't there's no like a density parameter you plug in here, right, Emma? So so density might impact um, the penetration, but maybe not the dominating factor here. So guys, what do you think will be the dominating factor here when the temperature changes? So if you look at the 1.4 and the 5.7, what have changed based on this equation? Did we change the microwave length, wavelength? No, okay. So how about epsilon single prime, the dielectric constant? Could that change? Actually, the dielectric constant, those dielectric properties. So both epsilon single prime and tangent loose, they represent the dielectric properties, right? So actually, these properties, how the molecule interact with the microwave, that property can change at different levels of the temperature. Because in the at the beginning of the class, we talked about the thermal energy is all about the microbial, the molecular vibration, right? So those vibration is actually dependent on temperature, and also those dielectric constant, those how much energy that absorb is also a function of temperature. Okay, so here probably you can see at higher temperature the penetration depth goes much deeper, right? So that is caused by the change, the evolution of those two terminologies. Okay, but I'm not going to explain why that will change because it's too physical chemistry, and probably I only understand some only partially of the knowledge. So if you're interested, you can look into why that actually is the reason, but it's probably two of the physics. Okay, in terms of food, we need to know what we need to know is that when the food is cold, the penetration depth is very we can only heat up the shallow part, but when the food is heated up, the energy can go through more in depth. Okay, so that actually will based on this information, what do you think we need to redesign our microwave processing system? If we have, for example, a food with 10 centimeter, if we start heating at 25 degrees C, there will be more problem with the inhomogeneous heating, right? So probably in that case, we need to involve one more step, that is preheating, right? To bring the temperature to maybe 40, 50 degrees C, and then put them into microwave so that we can reach more homogeneous heating inside the food, right? So that's something that we can, as food scientists, we can grab from those their physical property, those very complicated dielectric constant, those information, right? So what do you think other things we can think about or other take-home message we can have based on those properties? If you are asked to design a microwave assisted processing line. Okay, I will leave that question to you in the breakout room and homework, okay? So we'll probably need a little more time to think about and digest here. Any questions here, guys? This is a little bit difficult part, right? Any questions? Okay. So here I'm listing the food, different foods at different and their different penetration depths. Okay, for example, water. Okay, so those different values, they are measurement under different wavelengths and different conditions. So typically it's a range because we have run the experiment several times by different people, and you see they're quite different, right? So you see that for those like quartz, the penetration depth is huge, right? Because quartz is not very responsible to the microwave heating. Basically, in the previous table, I showed you that quartz has very small tangent loss value, so it doesn't really interact with microwave. So it's almost like transparent, okay? Just like a lot of microwave, a lot of other wavelengths, like visible lights, they can pass through those glass very easily without being blocked. So that same thing happened with those small wave, larger wavelengths as well. Okay, and some of them, especially high water content, they are very responsible to the microwave. With those ones, they have very small penetration depths. And here's the ice. Ice is very interesting. It has huge microwave penetration depths. Okay, so that's so when we are using the microwave to heat up frozen food, that's something that we can consider. Maybe once it's frozen, the penetration depth it's becoming a less problem. It can probably heat up the entire food very well. Okay, but really depending on other properties as well. For example, it has some fat on it. The fat might reduce the penetration depth, right? So there are a lot of things that we can consider based on the composition of the food material. So that's why it's hard to predict all the food material, even with different batch, or they are very sensitive to the penetration depth. So here I want to show you a very interesting experiment done by a scientist. Okay, so I don't know why it's not playing, but let me play here. So this is
the kitchen where the new boyfriend will unofficially become.
So this is a very exciting, very interesting experiment showing you how magic the penetration depth is playing during the microwave. This was a very famous experiment done in 2 years ago, and the scientist was just able to explain why this is happening. Okay.
If you don't know about grapes in the microwave, you haven't been keeping up with the internet.
All right, so we're gonna do this grape in a microwave experiment.
For 20 years, people have been microwaving 2 grape halves connected by a bridge of skin to create sparks, light, plasma.
Oh, there's a lot of juice from these, actually.
A plasma is a superheated gas in which electrons have been stripped from the molecules. Lightning is a common example. So, how do you get that from grapes? Amateur explanations focused on conducting electricity between the two halves. The skin bridge was the key. Or was it? Scientists who have now investigated the grape plasma phenomenon in depth say no. You can use two whole grapes as long as they touch each other. And the explanation has to do not with conductivity, but with microwaves being trapped inside each grape. Here's what happens. The wavelengths of microwave radiation are about 5 inches. But water, which is what grapes are made of, compresses these wavelengths to about 1/2 inch. That's about the same size as the grape. So the microwave radiation bounces around inside the grape and concentrates in the center. That's called resonance. With 2 grapes, or 2 spheres of a hydrogel, mostly water but no skin, the concentration is where the 2 meet. There's such a strong electromagnetic field at that spot that it sparks a plasma by stripping an electron off a sodium or potassium molecule. That triggers a cascade of other atoms in the air losing electrons as they absorb microwave radiation. But that's not what really excited the scientists. They were interested in the hotspots where the grapes meet. You can see them in red. The microwaves in that region were about 80 times smaller than in air. And that was a real surprise to the scientists because water worked on microwaves in a way that had never been seen. Now, if a substance could be found that would do that with visible light, which is so small it's measured in nanometers, that could have great implications for microscopes, research in computer chips, and other areas. So never assume a party trick is just a party trick. Not if it involves a microwave.
Okay, that was awesome.
Wasn't that cool? So that was a really, really interesting study that was done very, very recently because people found this phenomena for decades, but scientists were just able to explain what happened there. So if you're interested, I can post more resource for you to read. Basically, it's a trap of the microwave inside those very unique geometry. So that's the fun part of the microwave, okay? And let me see. So here, because I just talked about the penetration depth, so most of the case that depending on the wavelength, the heating part is on the surface. But if you look at this this curve, you'll see that the highest peak, the highest intensity peak is actually inside surface, okay? The inside this material below the surface, right? So this is something more prominent when we are dealing with a longer wavelength, okay? So for example, if you're using the microwave to this small longer wavelength to process meat, you'll see that the heating part is a little bit below that, okay? And also there's a periodic accumulation of wavelength at a certain spot, and a very so there are several heat spots by those wavelengths accumulation. Okay, so that's why on those pizza you will see a different heat spot there. Okay, and the more towards the middle, then the heat spot is less prominent. But on the side, you'll see a very distinct temperature distribution difference. Okay, but if you are treating a bulk product, and then this penetration depth is less prominent. Okay, typically it will just start heating at the surface, and then the inside will be more a conduction heat. So really, depending on the food that you're heating, actually, it's actually different heating mechanisms, and you'll see a very inhomogeneous distribution of the heat map. So here I'm going to put you guys into breakout rooms for about 5 to 6 minutes. So basically I have 2 questions. The first question is that compared to the conventional heating, for example, oven heating, what do you think is the unique part here? Okay, and second, so based on this unique part, where do you think we can apply the microheating? So let me put you guys into groups, breakout rooms. Okay. And I'll meet you guys in about 6 minutes. Zoe, do you need help with putting into the room? Okay, welcome back, guys. Any of you want to share what your thoughts are? What are the unique part about the microwave processing?
My group said that microwave heating is
Mhm.
usually a lot faster than conventional heating.
Good. Veronica, why do you think microwave heating will be faster? So say if we convey same amount of energy, why is microwave heating it takes much less time than like oven, for example?
Yeah, so it's because the waves are able to penetrate the product at a faster rate. It takes quite a lot more time for the thermal heat to like conduct or convect into the product.
Good job. So we are using, good job, Veronica. So she's talking that we are using a very different heating strategy to heat up food, right? Conventionally, we heat up the surface and then the surface will pass along the energy into the internal structures. But right now we're directly heating below the surface so that we kind of skipped that heat transfer part, right? So in first case, in the first scenario, we need to first heat up the surface. And then once the surface is heating up to a certain degree, then it will cause a temperature gradient. And that temperature gradient helps the heat to keep penetrating. But right now we are creating the hotspot inside the food so that that can kind of radiate to the heat to the nearing part, which is much more efficient, right? Good job, good job. So any other thoughts? Okay. So I think that's the major one. Okay. So based on this feature, where do you think we can apply this microwave in food industry? What are the processes you think takes way too much time? For example, cooking we just mentioned. What are other processes you think can be speed up by the microwave? Any thoughts or guess?
What about like steaming?
Steaming. Can you talk more about it, Abby?
Oh, I was saying something else.
Sorry, Abby. Well, for steaming, like usually I put it in a strainer in a pot, like over the stove, and it takes a while. But in the microwave, you can put saran wrap over what you're cooking, like peas, like frozen peas or something, and kind of steam them quicker.
Yes, that's a very good suggestion. I think it starts. I see some of the application in the steaming, like blanching of the microwave, right? Especially it's approved in Europe recent years. Yeah, that's a very good suggestion, Emma. So that also is one of the potential application. Any other thoughts?
I was thinking in package sterilization, just because it
Oh,
takes
yes.
from the outside in.
Right. Sterilization also takes way too much time. Good job. Okay. Yeah, so the one that I'm going to cover today is quite different. Okay, so it's related to drying. So drying is another very slow process if you think about it, right? For example, air drying takes a long time, but spray drying will only able to, it's only suitable for powder foods, right? So here, if we use microwave assisted drying, so here I'm showing you the comparison between the first one is the microwave assisted drying, and second one is hot air, freeze drying, and the vacuum drying. So the y-axis is moisture content. So the more steep is the curve means the faster drying process, right? So the microwave assisted drying is on the most left side. So this one is the microwave drying. So way much more efficient than others. So that's one of the application. Okay. So why do you think microwave can speed up drying process for so efficiently? Why is that? So think about when we are drying foods by hot air, what will happen? How about the surface? When you, for example, you're drying the surface will kind of will be dried first, for example, right? And it will be forming something like a crust, right? And then that crust can probably shrink. So how does that impact the following steps? Do you think when the crust formed, do you think it's fasting the making the process faster or slower?
Wouldn't it slow down the drying process because like all the moisture is stuck on the inside?
Yes, Lauren. So when we are creating that is the crust, we actually blocking the moisture from evaporating, right? So that's something that really is the main hurdle that for a lot of drying process, because all the heat is applied externally, right? So basically in all the heating, we are always heating up the surface and then pass the heat to the inside. So that actually causes, one thing is that it's called internal heat resistance, which is the time that it takes to penetrate the entire food. You guys did the calculation about thermal lag factor in the retort, right? So that's all about the resistance of the heat penetration. And the second is the formation of the crust, right? Also stop the water from evaporation. Okay, so in our case, if we use the microwave process to drying food, we will actually create a hot spot inside the food, which means the internal pressure will be greater than external pressure. That can actually push the water out of the food itself and create some porous structure to speed it up. Okay, so there are several ways that, or several mechanisms the microwave can help to speed up the drying process, right? So that's why it's so efficient, okay? That's one of the areas that we have seen more and more applications of microwave assisted drying. But the problem is that the machine is still very complicated. Okay, so in the homework, I will let you guys work on the microwave baking, okay, as a comparison to the conventional baking. You'll probably discuss some difference in color development, texture difference, and some chemical reactions happening inside during the comparing the conventional baking and the microwave baking, okay? So this is the article that probably will help you better to understand the difference. Okay, so before we finish, I'll briefly talk about what we'll do for this Friday's lab. So we have two tasks. The first one is to measure the microwave power. Basically, you'll use water and heat it for different amount of time. And finally, we measure the time difference. And based on that, we'll calculate how much microwave density, microwave power density is that. Okay. And second, we'll measure the penetration depth. So basically, we'll use a very big chunk of cheese block or potato and heat it for different amount of time. And then we will use thermometer to measure where it's hot spot first. But it might be difficult to get that number because they could be very similar. Okay, and our thermometer is not very sensitive. So the hotspot is very difficult to get, but we can get the penetration depth basically to plot it out how fast the microwave decay inside the food. Okay, so those are the two tasks that we'll be working on this Friday's lab. Any questions about today's class? or any question about the lab or the seminar or the homework? Okay, so I'll be posting those stuff on Canvas, especially the homework. I'll be posting it very soon after this class. And for the lab handout, I might still take a little bit more time to polish it before posting it. And for the seminar, I will post the rubric to you before probably tomorrow. Okay. So if you have any questions, you can stay in Zoom. If not, then I will see you guys on Thursday. Right.